and welcome. Here we are at section 4.3, and 4.3 is about rate of change other than motion. So we're going to look at kind of everyday situations. When can we use a derivative and what information does it give us? So the first thing that I see on our notes is increasing or decreasing. Could I tell if my height is increasing or decreasing? Yes, I could. I could check the derivative. So to know if something's increasing or decreasing, check the sign of the derivative. So if my height were increasing, it would be because I have a derivative that is positive. And height, I'm going to call it my h function, so that h prime of t was greater than 0. Okay? Or height's derivative is greater than 0. What about the velocity is decreasing? Well, we found out velocity is decreasing. We would look at the derivative of velocity, right? So v prime would be less than 0. What about my IQ is increasing? Well, then I would need to check the derivative for Mrs. Oppold. Mrs. Oppold's derivative, IQ derivative, we'll get really specific, IQ derivative would have to be greater than 0 for my IQ to be increasing. So the next one's just kind of exhibit whatever we're talking about. Could be your heart, your love, your emotion, your bank account. To determine if it's increasing or decreasing, we just look at the derivative. So heart's derivative is less than 0. Okay? So it's pretty easy to tell if a function is increasing or decreasing. Just look at the derivative. Next, recall the derivative on a calculator. So, do you remember how to take a derivative? Find f prime of 3 on your calculator. And you know what? I see one typo. Let's back off because otherwise we're going to be finding the derivative of the derivative, and that's not what I intended on this. So just take that back to just f of x. Let's start with f of x. We want to get to f prime. So I will key into my calculator 5 sine of x. Let me grab my calculator. And let's walk through those steps one more time. I think most people are familiar. There are 2 places to get numeric derivative on your calculator. You can hit alpha, window, option 3, and that will give me a derivative. So I'm going to do that again. Alpha, window, option 3, and I'm into derivative dx. And then I'm going to put my function f, or 5 raised to the sine of x of x. Nope, we're evaluating at 3, so we put the number that we're evaluating right down there. It won't work if you put x there. And I get negative, so f prime of 3 is negative 1.999. That would be accepted by the AP. Also, because of that 6 after it, we could put negative 2.000, and that also would be an accepted answer. You can either truncate or round. The other option to get derivative, numeric derivative, is hit math option 8, and there you've got the same exact layout. Very good. Next, it says, is the function already a rate? Sometimes it can be difficult to tell, and you just have to read very carefully. So in this example, it says, if b of x is the bunny population after x years, then what is b prime of x? In this case, b prime of x is the rate of the bunny population, correct? B of x is just bunny population. B of x is bunny population. So if I take b prime of x, now I'm getting the rate of the bunny population. Okay. And it doesn't really ask for, but we can give units. So this would be in bunnies per year, wouldn't it? That would be the rate on that one. The next example says if b of x is a rate at which the bunny population increases, then what is the derivative of b of x? So here I know that b of x is already a rate. It's like it's a derivative. They just didn't indicate it with a derivative sign. And that's okay. You just have to read what the function stands for. So b of x is the rate of bunny population. So that would be in bunnies per year, of course. So if I go in and ask what b prime is, b prime of x ends up being the rate of the rate, doesn't it? The rate at which the rate of bunny population is changing. The rate at which the rate of bunny population is changing. So I'm going to get bunnies per year per year. So I'll have bunnies per year squared. Okay. Down at the bottom, rate of change from a table. Let me erase that last screen. Rate of change from a table. So we're given a table. I notice I've got years, I've got people. They want us to estimate P prime. So P prime of 15 would be dP with respect to the independent variable t. So I'd have dP dt evaluating at t equals 15. And we want to estimate. So that means we're going to draw in the estimation symbol instead of equality. You've done these before. So I'm going to take 15, which sits right between 10 and 20. It's a symmetric difference there. So I would have P of 20 minus P of 10 over 20 minus, over 20 minus 10. And that would equate to what? 150 minus 120 over 10. So it looks to me like I'm going to get 30 over 10, or 3. Label P over T, so people over years. So people per year. And that would be an approximation on that. For B, it gets a little trickier. 15 was nice. It fell right in between. But what about 20? 20 is right here. But this isn't a derivative there, is it? That is the number of people. So that is not a rate. We want to take this to a rate. So there's actually 3 ways you can handle this problem. You can work 30 and time 10 and do it that way. So I could do P of 30 minus P of 10 over 30 minus 10. Did I get an answer? I didn't calculate out the answer. I could also estimate, I could use 20 and 10. So I could go P of 20 minus P of 10 over 20 minus 10. And the final way is I could use 30 and 20. I could go P of 30 minus P of 20 over 30 minus 20. Any of those 3 are accepted ways. I tend to like the one I like the most. Why are we not getting a highlighter? I prefer doing that and just keep using like symmetrical difference, because I've got 10 above the 20 I'm targeting and 10 below the 20 I'm targeting. But honestly, any of them will work. All right, that was enough review. we can use our calculator on many of these, so grab your calculator and we'll go through them. Speedville High School opens its doors for students at 8 a.m. each morning. On one particular morning, the number of students inside Speedville High School can be modeled by the equation P of t equals 25 natural log 3t plus 1, where t sits between 0 and 8 minutes since the doors open at 8 a.m. Find the rate that the number of students inside Speedville High School is changing at 8:03. Okay, so we know we're on a time frame of 0 to 8. We have a function modeled there, and that's the number of students coming in. So that is not a rate function, is it? That is the number of students entering the building at 8 o'clock. And at 8:03. And we were in minutes, so I'm 3 minutes beyond 8 because 0 would correspond with 8 a.m. So I want P prime of 3 is what I'm after. And I realized that taking the derivative of this would not be all that difficult, but since it allows me to use my calculator, I am going to use my calculator. So here's my calculator. I have, just to save time, I've already preloaded this particular function. So you can see my y1 has 25 natural log 3x plus 1. So in my y1, I've got this equation stored. So that means I'm going to go to the home screen. I'm going to go alpha window option 3 and get the derivative. And I want to take the derivative with respect to x. And I'm using y1 equation, because that's where I stored it. And I want to evaluate it at 3. So I get 7.5. 7.500. Remember, we always need 3 decimal places, and I don't think it hurts to put those extra zeros on there because we are accurate out to thousandths there. And find the rate at which this time. So this would be students per minute. Seven and a half students entering the building. And it's positive, so that means, yeah, the population's increasing inside the building, which is what you'd expect at 8 a.m., right? Find the rate. And then if I wanted to write it out, I could say the number of students. Did I say, yeah, it's Speedville. The number of students at Speedville High School is changing. I would almost insert the word increasing because it's positive, and it just gives a little bit more information. Is increasing at a rate. So if we talk about a rate, we know we've done a derivative at a rate of 7.500 students per minute at, and then we can say, I'm going to say at 8:03 a.m. Okay. Or you could say at t equals 3. That would be fine too at 3 minutes. But there we go. So not too hard a problem. I'm going to stop my recording and I'm going to re-record or pick up on the next one and see if I can speed up my machine a little bit. Okay.